Good morning. My name is Khushi Kankaria, and the story I'm sharing today begins with a simple question of trust. In genomics, we are often taught to accept metadata as the ground truth. If a file is labeled bovine muscle, we assume the biology inside is bovine. But today, I want to present a case where the sequence data challenged that assumption. I'm going to share my analysis of sOTU U145189, a cryptic viral signal that we propose represents a Trojan horse hiding within the host transcriptome. To understand the anomaly, we have to start with the dataset first. We analyzed transcriptomes from Mewa yaks grazing on the Tibetan Plateau. The original study was designed to look at high altitude adaptation. Crucially, these sequencing libraries were poly A selected and were designed to capture host mRNAs and not viruses. But when you sequence a tissue, you sometimes capture transcripts from everything present in that tissue, and that is where we found the contradiction. We recovered a near complete viral genome, sOTU U145189, which belongs to the family Toteviridae. This discovery raised two immediate red flags. First, Toteviridae are double-stranded RNA viruses lacking poly-A tails. Under standard protocols, they are not expected to be efficiently captured by poly-A selection. Second, these viruses typically infect fungi or protozoa, not mammals. So we had to ask, why is a tailless non-mammalian virus appearing in a tailed bovine dataset? And while contamination was considered, the consistency and tissue specificity of the signal argued against it. Instead, we proposed an ecological hypothesis, the Trojan Horse mechanism. We postulated that the virus isn't infecting the yak directly. Rather, it is likely infecting a parasite, Sarcocystis, which is known to form cysts embedded deep within the muscle fibers. If this model is correct, the viral signal shouldn't look like a systemic infection, but should track the parasitic burden. To test this, we treated the sequence reads as forensic evidence. We used serratus to assess global occurrence and AlphaFold to evaluate whether the assembled RdRp encoded a structurally plausible polymerase. The ecological distribution provided our first line of evidence. When we screened archival data, we found the virus in 14 independent bovine libraries. Crucially, look at the tissue tropism. The signal is restricted almost exclusively to striated muscle and heart. In metabolic organs like the liver or lung from the same study cohorts, the virus is undetectable. This absence of systemic signal argues strongly against direct bovine infection, but matches the encystment niche of the Sarcocystis parasite. But we still needed to explain the technical artifact. How was a dsRNA virus captured in a poly-A library? AlphaFold confirmed the protein structure is a valid RdRp, but upon inspecting the nucleotide sequence, we found a potential mechanism. At positions 614 and 695, there are internal adenosine-rich tracks, which are AAAA motifs. Our analysis suggests these regions may act as false tails, enabling internal priming by oligo-DT. This offers a plausible explanation for how a tailless virus leaked into this specific dataset. Finally, to confirm the host identity, we looked at the evolutionary relationships. Our phylogenetic analysis places U145189, our virus, in a robust sister clade with Leishmania RNA virus 1, a well-categorized protozoan virus. This phylogenetic placement is inconsistent with known fungal totaviruses and is most consistent with a protozoan host. So, what does this finding offer the field? Ecologically, we believe we have identified a hyperparasite that was hiding in plain sight. But perhaps, more importantly, this virus could serve as a digital biomarker. This suggests that we could potentially remine terabytes of archival livestock data to measure parasitic load without ever returning to the field. It suggests that SRA is not just an archive, but a reservoir of unasked questions waiting for this kind of forensic analysis. Thank you.